Rajesh Kumar received his BTech degree from NIT Kurukshetra, India, and the MTech degree in Power System and PhD degree in Intelligence System from MIT Jaipur. He was postdoctoral research fellow in Department of Electrical and Computer Engineering at the National University of Singapore from 2009 to 2011. Currently, he has been working as a professor with Department of Electrical Engineering at MIT Jaipur. His research interests focus on intelligence system, machine intelligence, power management, smart grid, robotics. He has published over 550 research articles, has supervised 20 PhD, more than 30 MTech theses. He has 40 patents to his name. He received 3 academic awards, 15 Best Paper Award, 6 Best Thesis Award, 4 Professional Award, 30 Student Award. He has received the Career Award for Young Teacher in 2002 from Government of India. He has been on 12 journal editorial board. He has been an associate editor of IEEE Access, IEEE ITEN Industrial Electronics Technology News, associate editor Swarm and Evolutionary Computation, Elsevier, associate editor IET Renewable and Power Generation, associate editor IET Power Electronics, associate editor International Journal of Bio-Inspired Computing, and CAAI Transaction on Intelligence Technology, IET. He is an senior member of IEEE USA, Fellow IET UK, Fellow IE India, Fellow IETE, Life Member of CSI, Senior Member of IEANG, Life Member of ISTE. He was Honorary Secretary of IETE Rajasthan Chapter and XCOM IEEE Delhi, PESIS, and Vice Chairman of IEEE Rajasthan Subsection. So from this short introduction about Rajesh sir, now over to you, Rajesh sir.
Yeah, hello. Good morning to everyone, and thanks, Dr. Anupam, for introducing me to various participants here. I hope my voice is clear. And
Yes, sir, voice is clear, sir.
okay, so I'm sharing and just confirm it that okay, the PPT is visible.
Yes, sir, it is visible now.
Okay. So good morning to all who are here. So today we have our discussion on intelligent controller, and in this 1.5 hour or so, our discussion is uh, we start with basic controllers, and then we move on to fuzzy controllers or neurocontrollers, and then some advantages. So just to understand the whole process, what we do today is we take a case study and then keep on discussing the various types of controller, then impacts of those on that particular problem, so that we can have both understanding of the problem as well as the how the controllers they behave, and then if you develop any controller, then how to analyze that particular controller. So discussion consists of following things there. Don't know it is working or not. Yeah, so we start with the basic controllers, PID controllers, in a very compressed manner, and then what are the different types of PID controllers people use, maybe in drives, power electronics, or electrical applications, or in robotics, wherever you can think of control is required. These are common controllers, conventional controllers. Then the next challenge we discuss that how to tune them, because that is really a big challenge to tune the parameters of controller. So there also we can use conventional approach as well as intelligent approach to find out the parameters of these controllers. Various categories: auto tune, self tuned, intelligent tune. So these are the tuning uh, procedures that can be adopted to tune the PID controllers. In intelligent tuning, we can talk about fuzzy based tuning or neural based tuning or genetic based tuning and so on. You if you search on the various academic platforms or research uh, arena, you'll find that thousands of people discussed about tuning of these controllers. So they use some convention, these kind of approaches, or they use some meta heuristic kind of algorithms to tune these controllers there. Then another class is there which is known as slide mode controller. A small discussion on that one, what are control laws and how it works. And then we discuss in detail about the fuzzy controllers. We talk about structure of fuzzy controller, fuzzy PIPD, PID like controllers, adaptive fuzzy controllers, and then what are the main factors when we talk about adaptive fuzzy controller, what are the main factors which are important when you are designing fuzzy controllers, like scaling factors and membership functions. And if you have membership function, then subcategorizing them, symmetrical membership functions or unsymmetrical membership functions. And then we will discuss neural controller, what is that, and then uh, uh, most of you are aware of it, but just to check it, like how we can use your ANN or ANN architectures for control purpose. And so we'll discuss a neural controller, online neural controller or offline neural controller. And then some advancements of where we are mixing the two controllers. We are mixing the properties of fuzzy and neuro. Reason being, each of one is having a one kind of advantage and disadvantage. So if we mix them, if we combine them, can we compensate the disadvantage of one by adding the second type of controller? So there we talk about, we'll try to understand fuzzy neuron, what it is there, what is neurofuzzy, this, what's the difference if I switch these two terms, fuzzy neuro or neurofuzzy, how it make a difference, what is the difference in the controller. Then adaptive neurofuzzy system controller, again we'll discuss about symmetrical and unsymmetrical controllers there. And then at the end we'll see that how if you develop any controller, how you can check the performance of these controllers, like which one is good. So if you want to claim it, like, okay, you have developed certain kind of controller for certain application and your controller is better, so how you can put it in on a record that, okay, why your controller is better, what are those parameters. So we'll talk about transient and steady state analysis with different conditions there, and then finally we conclude over these controllers. So this one is the flow of today's presentation. So I start with a small problem, and the problem is basically, say it's a robotic problem or a electric drives problem, or it's a you can consider the same as a paper industry problem. You can say consider same as uh, your cloth mill problem. That is basically, we have some rotating machine, okay, and we want to control the speed of or motion or angle of that particular machine by certain kind of a mechanism. So we need a source. We need a source to power it up. So the source is basically of it's a kind of uncontrolled kind of source. Like we have some constant source there. Then we need a power modulator which uh, modulate our source according to our requirement. Say maybe your source is DC, but I need AC, so it convert DC to AC, or likewise. And then if since you are using a power modulator, you need a control unit. So control unit basically control that modulator, the processing of it. And here comes the controllers. The controllers, they are the part of this control unit. So we give a reference trajectory that, okay, this is what I want from my system. Okay, maybe say if it is a robotic problem, so I'll give that reference signal or reference trajectory that, okay, the angle at that instant to be 30 degree. So that as a reference signal goes to the control unit. Control unit, based upon this reference signal and feedback, generates some signal. That signal moves to the power modulator, which modulate the power, and that modulated power moves to the motor, and the motor then rotate according to that one. And we have feedback mechanism. We sense it and give a feedback to my control signal. So control signal always works on the feedback system, feedback mechanism. Just 1 second, let me minimize it. Yeah. So control system always works on the feedback. It will have a feedback from the system, how the system is behaving. It can be any process. So this one is one kind of application, but it can be of any process, maybe your industry, any industry process, which is most of the processes are control process, closed loop control process. So this one is the feedback, and this one is the reference signal, and here is the controller. So the job of the controller is to force the whole process according to our requirement, according to our desired outputs. So that is the job of this particular section there. So this one is a diagram of any drive system, maybe as I told you, electric drive or mechatronic drive system or robotic drive system or something like that. So when we are talking about today's okay, just our focus will be on this this part, which is let me highlight it. So our focus is on this part, that is a control unit, because most of the other things, they are physical structures which are there. So we need to develop a certain kind of unit here which control the whole of the process. Okay, so we are starting with P controller. That is the simplest controller people are using, that can be used. So P controller, when we try to define in mathematical term, here your E is there. E is basically error. We define in control E as error, and this is error between your desired, what you want, and actual. So the desired and actual, they generate certain error, and you have seen in the block diagram, this one is a feedback to your control block. So this one is there, and the output generated by the block will be u0, some initial value, plus the signal is proportional to your error. So this is what it is generated if you are using a P controller. And I'm not going to the mathematical part of it. Sorry. But this one is the process. If you want to plot output signal with respect to error, okay, you have some u0 cut, and then it is proportional finally at till certain end, and after that we put a kind of cutting or so that it can't be a kind of infinite structure. So the output characteristic, input output characteristic of P controller is like this. So what are the advantages of using this if I use it? Okay, the advantages of using this type of controller, it has small steady state error. Okay, and steady state error means when my transients die out, with time, and my system is behaving in a constant operation. Okay, with time kind of structure. So that is one, and then dynamics is very fast. The reaction is very fast because there is no any delaying element here in this equation. Whatever be the error, it is gained, it is amplified by a certain value, and that will be the output signal. So it is very fast. So dynamics achieved from such type of controllers are very fast. But there are some disadvantages, and the disadvantage is basically this one, that you can reduce the error but you cannot eliminate it, because if we go by the order of the system and we try to calculate steady state error, it comes 1 over 1 plus kp, the value. So kp is whatever is the value there, or whatever is the value of kp, you cannot make your e as a steady state error 0. You need infinite value of kp to make it 0. So that is not a that is a problem with this one. So it reduces the error, but you cannot eliminate it. Okay, so this one is just to justify that theory. I have simulated these things, and then just to see, if you see the graphs there, desired is 1. Okay, you can see the desired response. That means 1 means, okay, I want to rotate my motor with the angle of 1 degree kind of, or you can say, if you are looking for motion, I want to run my machine at 1 pu per unit scale. 1 pu is, that is basically you have decided a maximum of say 1000 rpm, something like that. So you can see the response of the system. So if KPI is 2, you can see here there is a large gap between in the steady state operation. Okay, say at 2.5 there is a large gap. I want 1, but it is settling somewhere around 0.65 or something. But as you keep on increasing your KP, you can see that this error keep on reducing. That is what we have there in our comment box also, that if you increase the KP it reduces, but you cannot eliminate it. So this one is the first basic type of controller from where people started basically. So this one is a 3D diagram to give you a better picturization of the same stuff, nothing new in it. Then people come out with certain new thing. So this one is pure mathematics, and then okay, those mathematical things are programmed in a nice manner. The next one is PI controller. So I controller is basically integral controller. You can see that the term, the equation is now modified. Equation, you can see there is one term which is E of t, which is already there in proportional, plus one another term is being added here. And what we are doing here is we are taking the integral of error and kind of structure. And that is basically, now I have two terms. One is Kp into Et. This is P controller. And another one is Kp by Ti, and integral term. This is known as integral. So when you combine these two, that makes PI controller. Now you are integrating the errors, and based upon those you are generating the output. If you do so, okay, this one is control system analysis, where we can talk about, okay, stabilizing and destabilizing effect and the transfer function. So and not a major agenda for here to understand, but let's check about, okay, how it is working and what are the advantage and disadvantage of this one. So the advantage is, like, now your steady state error can be 0 because you have added the integral term to it. Earlier controller, that was suffering from steady state error, you cannot eliminate it, but here you can eliminate the error there. And then here the negative point is basically stability. So these are control system approaches. You can check it. Your graph is moving towards -1 plus j0, and then we have destabilizing effect. And obviously also, like here you are this one is creating a issue over stability. I'll show you on the graph that how we can judge, how we can uh, comment on this one if we have graphs in front of us. So these are the graphs, and you can see here in this graph Kp is fixed. Let me share with you. So Kp is fixed. I am just changing my Ki. So if my Ki is less, so you can have a graph like this. Now this one is like Kp is dominating basically. So Ki is less. So okay. Anyway, it is going and trying to reach to 1, but it will take a lot of time to reach. In general or in practical, we don't want our system to respond so slowly. It's like, okay, if I am working on a robot which is being used to operate a patient in a hospital, so what I want is, as soon as I give a command that, okay, rotate 30-degree, and then I'm giving command to cut, so it goes to 30-degree and then do the operation. We never want that robot take, okay, 10 to 20 minutes to reach to 30-degree and then perform it. Then if it is like that, then the patient will be in danger and all those things will be there. So this one is not a good idea, taking Ki is equal to 1. So what we are doing is we are increasing the Ki, and to see that, okay, around 3 seconds it is stabilizing at 1. You can see here. But what is happening if I'm increasing the Ki? You can see here the peak desired is 1. So what the system is doing, system is going, and it's going beyond 1 and then coming down, and then so the system start oscillating. And that's why we are saying that, okay, if this is happening, you have stability issues. Well, in this case it dies out very fast, but it may be possible in some applications you have more oscillations and then settling down. So the advantage of Ki on one side, it is, if I see the picture here at 4 t is equal to 4.5, there is no any steady state error. But at the same time, I can see here there is overshoot. Your system I want 1, it jump to first 1.2 and then settle down. So that's a one kind of effect on if I'm using PI controller. Because we need to understand this one so that we can understand the controllers fuzzy and all those controllers later on. So you can say it's a spiky, it's a peaky basically. You have peak and then it settles down. Third one is your PD controller. So here you can see what is being added. This one is first is your KP into ES, that is old P. The second term you can see now TD is multiplied here, that is basically derivative term. So it is a combination of proportional. Added term is a derivative of the errors basically. So this one is the output, and if you do use it, you can see that it is reverse of the earlier one. Earlier it has a destabilizing effect. This one is have a stabilizing effect. Okay. So this one is a good. What is good here? It avoid sudden change in the error signal, and it improves the stability of the system. PI where try we PI where moves towards destabilizing zone. PD improve the stability of the system. Okay. And then it issue with this one is because the derivative means the change in the signal. Okay, derivative means xn minus xn minus 1, and that is being added to the system. So if there is a noise in the system, it amplifies the noise. So that is a big issue with this one, this type of controller. So each controller is having some advantage and disadvantage, and like also it cannot eliminate the error. It can reduce, it cannot eliminate the error. So these are the various graphs that can be achieved with here KD is fixed and KP is varied. So we need to see that what is the impact of you have fixed one of the parameter and change the another parameter. Uh, uh, KD means this term. Okay, KD means KP into TD, and KP itself is KP. So what is the impact on the performance? So if I fix that one and if I vary the KD, so you can see the change. So the change is occurring in the transient part. This is my transient part. This is steady state. So if you see the steady state, then n minus 1 is 0. So there is no effect here basically. Okay. Derivative term here it is 0 because it's a constant kind of line. Where is the derivative exist? Derivative exists in the transient part. This one is my transient part. So if to understand it, what is the impact? I have just zoomed this section, and you can see here by varying your KD, what will be the change in this one. So if I keep on changing the KD, it try to make it as fast as possible, but you can see at the same time it is stabilizing or steadying. I mean stabilizing somewhere 0.67 or 68. It is not reaching to 1. So that's the issue with this controller. So I have now three things with me. I have P, I have PI, and I have PID. P is okay, it's very fast, but steady state error is 0. Not cannot be 0. PI is a good one. It makes steady state error 0, but it introduces stability issues. PD is okay, it amplifies the noise, but it stabilizes the thing. So each one is having advantage and disadvantage. So then people think of why not to combine these things. And this is the combination here. You can see the combination. We have three terms, okay? KP, this one is proportional. KP by T1 Ti, this one is integral, and KP into TD, this is your derivative term. So this type of controller is known as PID controller. And these are the graphs more related to control, but what are the advantage and disadvantage we can think of. Okay, if KP increases, natural frequency increases, damping reduces, oscillations increases. KI increases, steady state error reduces, damping reduces, oscillations increases. If you increase KD, damping reduces, increases, oscillations decreases. Now each one is having something good, something bad. Now you can make a combinations of these three values, KP, KI, KD, to achieve it. Because see, if you increase KI, your oscillations increases. So we don't want oscillations. Oscillations means, okay, I give a command to my robot to move 30 degree, and what it is happening, it move and then it start oscillating around 30 degree, somewhere goes 31 to 29 and keep on oscillating, which is not required. I want it should go to 30 degree and remain at 30 degree. So so if I give, if I give certain command and say my tuning is not proper, so what are the issues? One issue can be uh, it move and it never reach to 30 degrees, settles somewhere around, it moves very fast but remains somewhere around 28. So that is basically your first part. Your KP is good, so it moves very fast but it never reaching there. Then what you have KI is also introduced there. So what it is making, okay, it reaches to 30 degree but it start oscillating between 31 to 28. Then you can tune your KD in such a way that you can reduce the oscillation. So these, changing these values of KP, KI and KD, that is known as the tuning of the parameters. So these are the various graphs that can be obtained, like what I have done here is keeping one constant and varying the others. So what are the graphs and what are the impacts there? So getting the best value of KP and KI and KD. Uh, KP is, again I'm repeating it, KP is simple KP, KI is KP by TI, and KD is KP into TD. So how to get it? And getting the best values of KP, KI and KD for the performance of your system is known as tuning of parameters. So these are the parameters of a controller, conventional PID controller. So this one is one method which is classical method, old one. What people do is they use Ziegler's-Nichols closed loop method. Well, in this method, what they do is they take any system and then they oscillate the system. From there, they calculate the period of oscillation, this one, and ultimate gain. And from there, they try to calculate the parameters of PID if you're using PID, if you're using PI, or if you're using P. But this one is not a good idea. Good idea in the sense that, like, if I'm using a controller in my big huge process, or say in a robo, so nobody allow me to oscillate the system. Okay, so how to do these jobs there? Another issue is there. What will happen that with the time, my parameters are changing. If my parameters are changing, parameter of the system, they are changing, so obviously the function property, they are changing, transfer function changing, and then how I again do I need to do, means like I need to do again some oscillations to calculate these parameters and all this. So there are many other issues related to this one. So but this is very easy to implement, but yeah, you need to force oscillations on the system, and that create a problem. So then people thought of why not to develop certain kind of algorithm, so that can we make self-tuning, okay, instead of giving some oscillations. Okay, so self-tuning, this one is one of the way. I mean, uh, they change your KP, KID, KI and KD by some kind of a mathematical relation. Okay, that okay, I measure error from here, I measure the performance of PID from here, and then these two inputs I pass it to the algorithm, which calculate KP, KI and KD, and that those values can be given to the plant. So here, okay, in one sense, okay, we get rid of assuming or getting the values of KP and KI, KD. But now they depend on another parameters, which are, you can see here, your alpha and beta. So again, to get the optimal value, we need to tune these parameters, that okay, what should be the value of alpha and beta. But this algorithm, the working of this algorithm, because here alpha and beta, they are also function of time, they are also changing. So when we are working this with this such type of system, this one is online self-tuning. There is nobody to now, no need to do oscillations and all those stuffs. It is working automatically. Error is going from here. Performance output is PID is coming from here. Those things comes here, and then they can be used to find out the values of PID. But now again, now the new thing appears there. We have new terms. They're like we have beta here, we have alpha here, efficiency requirements. So we need a knowledge of new parameters, which is sometimes it's a difficult task. And these are the performance of uh, those uh, those self-tuning PID controller. Not a very interesting or very impressive, but in some cases it works fine. Then people thought of like, okay, can we use, instead of using that mathematical algorithm, can we use fuzzy algorithm here? What is fuzzy and all that, I'll explain the later slides, but just understand that how that can be used here. So they have taken the inputs as an error and pass it to the fuzzy environment, uh, and then this fuzzy environment generate output signals. Those signals are used to tune the parameters of PID. This one is not a fuzzy controller. Here we are using fuzzy method, inference system, fuzzy calculation or fuzzy set theory to tune the parameters of PID. Okay, it is robust and easy to implement, but there is a drawback, that is the knowledge base is required, uh, which is one of the major requirement when we are developing any fuzzy algorithm there. But the performance is very good. If you see here, you can see here the requirement is 1 and the system moves very smooth and it settles at 1. So this one is working very good, and these are the environments, because you see here, let me explain it again. This one is fuzzy. This algorithm keep on changing the parameters of PID with time. So every instant they get the value of error and change in error. Based upon that, they are generating the value of this fuzzy algorithm is generating the value of KP, KI, and KD, and those values are now then they are being used to uh, control the plant. So if you try to uh, plot the values, so you can see that error and change in error. This one is KP, this one is KI and KD. You can see that they are moving very fast. So this one is the variation in KP and KID, KP, KI and KD, and this variation comes in the real time. We are getting the input, we are calculating the error and change in error is moving to the fuzzy, and at every instant it is generating certain kind of outputs. And those outputs, it is generating three outputs, KP, KI, and KD, and they are given to the system. So this one is intelligent tuning of your controller. So another one, we are just keep on checking what are the working and procedures of various controller. Another one is we can use neural algorithm to tune the parameter. So for neural, yeah, you can see here now there is some change here. We are taking the input what is desired, and we are taking this one what is we are getting, and then we are using neural algorithm to tune the parameters of PI. Now there is a difference between this and earlier approach. In fuzzy, what we are taking the error and change in the error as the inputs, and it is generating certain output. Now here in neural algorithm, the errors are what is desired and what is the system is getting. We try to map we try to map the things like, okay, how better y can be same as yc, and then to do that we try to find out the parameters of PID. Well, what is the advantage of using such type of approach? The advantage is we can accommodate poorly modeled systems. If my system is poorly modeled, uh, and if it is a non-linear, it is dynamic system. So there we can use the power of neural network, and that is basically approximations and all those things which are already we are aware of it. So that power is being used here. So if my system is poorly modeled and dynamic in nature, this type of tuning works fine. But yeah, if you want to do the tuning, you need input output data pattern. So either you have pattern of that system already which is being used, or you need to see that, okay, how to get this type of how to get the pattern so that I can train my neural network. So this one is the performance of the system. Again, yeah, it is settling at 1, very good, and then response is okay, kind of things. This depends, now this curve here, this depends upon the data which we have received. We have simulated, and then we have synthetic data, and then from the basis of that we try to train it and then try to use it. If my data are much better, then okay, now some better performance curve can be achieved from there. Third one is just giving an idea, that is basically a genetic approach. So here, now this opens another lack of intelligence, which is inspired from the nature or species. So we can say meta-heuristic algorithms, or bio-inspired algorithms, or nature-inspired algorithms. So these are the optimization algorithms. So here just what we are doing, we are making some change in the structure of it. And what is the change? The change is that, okay, I take some parameter of my controller performance as my objective function, and then I try to achieve that objective function, either maximizing something or minimizing something, by varying certain variables. So variables are okay. Variables are known to me, because known in the sense that I know the variables, but the exact values are not known to me. Objective function key can be anything, like, okay, minimize the steady state error can be objective function. Another objective function is minimize your peak. Uh, Another objective function is increase the stability of the system. So there can be any kind of objective function, and to achieve that objective function, we can use classical optimization approach. But if we are considering my system is highly nonlinear dynamic, then classical approach fails there. And then people suggested that why not to go for materialistic or kind of approaches. So this one is one of them. The list is quite big. I think most of you are aware of that. We have more than Nowadays we have more than 500 such type of algorithms which are existing there, uh, starting from GA to PSOs to Gray Wolf and many more. So few of the things will be discussed in this course also. So genetic, what we do in the genetic, in just a simple way, I'm putting it like, okay, we fix few things, that okay, how much is my population, what is the crossover probability, what is the mutation probability, and we generate the random array, generate the population. And once we have this with us, then we do the encoding part. We have fitness function, and we have these three things, that okay, how we operate on these things: matching, pole, crossover, and mutation. And then we decode it. Okay, so the process goes like this: we fix these things, we encode the parameters, we calculate the fitness function, we perform these operators, and then it keep on running till certain kind of level of accuracy is achieved, and then finally we decode it, and that is given passed to the controller. So controller values there. So this is the whole flow, and this remains, means you just change this approach. Instead of fixing here population size, crossover, or mutation, you can fix it like population size, and then C1, C2, and omega. Rest things work here, and here in the operators we can have uh, your updation of velocity, and then decode it. So then this will be tuning using PSO approach. In another case, you can fix the number of walls, and then you can fix the parameters, that A1 and A2 and C1, and do these operators update the position. Then it will be a PID tuning using GWO. So you can apply any kind of approach there, and that will give me a optimally tuned PID controller. So this one is how it works. Those who are not aware of, just in a very small, fast way, I try to explain it. This one is a population. Okay, so written as parents. Population means all possible solutions. Okay, so this string consists of many values 0, 1, 0, 1. Likewise, So these are nothing but the KP, KI, and KD. So you can take it like this, that first 3 digit represent KP, and the next 3 represent KI, and last 2 represent value of KD. So this one is the combination. Basically this is one kind of solution which give me a certain kind of a performance. Similarly, this one is another kind of a solution. We operate two things there, crossover and mutation. Crossover means we assume certain point there where we swap the things. So you can see here at this blue line we are swapping the things. That means all blue, these blue 0 1 0 0 1 1 and 1 0 1, they that frame another new solution. And the bottom, this one 0 1 1 1 1 and 0 1 0, this is another solution. So we generate solutions from the solutions likewise. Okay, and then we check the fitness means how you check it. Now this one is a new solution. Okay, this is new solution where we have these three KP, and this one is KI, and this one is KD. We take these values, we put it into the system, check the performance. Say I'm just looking for steady state error, so find out how much is the steady state error and note it. Likewise, I have many populations there. From there we try to see that which one is most fit. That is basically fitness. This based on Darwin's theory of principle, and we try to use it. So not that today agenda is not to discuss more on genetic algorithm, because you have different speakers for that one. I'm moving a bit fast now towards fuzzy and all those controllers there. But this approach is used to find out what is the most optimal value. Mutation can be done like we swap any particular value there. So swap means like change it, like it is 0, we make it 1. If it is 1, we make it 0. This what we are doing is we are doing in binary. So in binary we do it like this. So this one is known as mutation. We perform the mutation to ensure that we are not trapped in local solutions. We are looking for a global solution. So that's just to avoid the local solutions, we perform mutations. And this, once this whole process is complete, we have new solutions, and then those new solutions will give us new values of PID, and those values of PID we again pass to the system like this. So this is how the genetic algorithm works. So it provides a good response for all system without any knowledge of mathematical model, and that's a good part of the system there. But it is a complex algorithm, and the disadvantage with this one is it is a probabilistic algorithm. It works on the theory of you use the probability there. Since it is heuristic in nature, so there are randomness at everywhere, randomness in the starting point, randomness in the crossover and the mutations, and likewise. So what is happening that every time if you run genetic algorithm the same set of same problem 1,000 times, it will generate 1,000 different answers. So there is a randomness in the solution. So then which solution is better? That is again a challenge there if you want to implement it real time. And then yeah, it consume a bit more time also, because for any instant, for any solution, you have, say you have some population, and based upon that it evaluate each and every part of it. So it takes some more time also. So that's why we are putting a complex algorithm. These are the performances which, so I will try to analyze it. We have different publications out of it. You can see here what we are trying to analyze is what is the variation in KP and KD if I move my two probabilities, crossover probability PC and PM, that is mutation probability. So what is the impact on my gains if I vary my probabilities there, and then you can have a response of the system. So similarly, you can apply, you can do more research in this area, like you can use, you have system equations with you, you are using PID controller, and to tune your PID controller, you can use any type of meta-heuristic algorithm, and then you can make these studies that what are the impact of changing the parameters of that algorithm on the performance on the parameters of the controller, and then once you know that effect of those parameters of the algorithm, the controller, then you can analyze what is the impact of the controller effect, parameters effect on the system performance, and then you can finally conclude what is the best combination. So this one is one kind of another domain or area totally which can be used uh, to 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 tune the parameters of PID control. Then another kind of a controller which is very popular, which is known as slide mode controller. It basically works on some control laws. Like PID, we have control laws, KP plus KP by time constant into the integral plus KP into time constant derivative. Like also here we have some some control laws which are basically mathematically related, mathematical in the like nothing like as such, uh, um, based on certain kind of intelligence. These are developed based on certain kind of uh, mathematical driven relation rather than some kind of a data driven relations. So here u is minus a phi, and we design it in this fashion, not major agenda, but I just try to give you certain mm, insight on this one. So it's a simple algorithm, and this one is insensitive to parameter variations. What is the issue with this one? Since we are switching here, okay, if s is less than 0, minus 1, if s is greater than 0, it is 1. There is a chattering. So this one I'll show in the graph what is chattering there. So this you can see there is a chattering here. The small, so these are not oscillation, but these are some vibrations comes into the performance of the system. So you can see here, if I vary these h gains, certain kind of chattering appears into the system. Because if I zoom them, you can see this one is known as chattering. So you can see that is okay, the system is reaching very fast to 0.99, but around 0.99 it is having certain kind of very indifferent behavior, and that is basically an issue of a slide mode controller. Then people modify this law. uh, this new law eliminates this chattering better, but it has a large steady state error. You can see here it is not settling to, not reaching to 1. Okay, and then they modify, they combine the two laws, earlier one and this one. So the new law is having combination, so it reduces the, you can see the steady state error also and the chattering also. And this is people, how people are working and all those things there. These are the, and people then again modify the control laws uh, to generate a better fast response. So you can see here the response is now fast and it is reaching to 1, and it is stabilizing here, no chattering, no kind of oscillations, and the system is behaving very nicely. Okay, so these all these methods are like PID and slide mode controllers, they are derived on certain kind of uh, model, certain kind of physical equations converted into mathematical form and all that. But all these models, they have issues related with the various gains, and then gains can be tuned by conventional approaches, or we can use some kind of some approaches which are taken from your intelligence, so we can call them intelligent tune controllers. Here also, in this case also, like slide mode, we have again gains. So how to get the optimal or best gain here? Okay, we have done certain analysis, we vary your d, and finally we reach that, okay, if d is 1, there is no any steady state error. But can we think of any auto tuning of these parameters and all this? And when we say auto tuning, we have to use all those techniques which we have discussed earlier. So now the next category, which is important and which is very popular, a very stabilized one, and that is fuzzy controllers. Just one second. Okay, so here what we are doing is we this controller is designed on the basis of few things. One is the what is the knowledge you have, what are the reasoning, how you are designing the reasoning of your whole process, and it is not basically model based, purely model based. It totally, it depends upon the knowledge as well as the thinking, human thinking. And what the good part is, they are very simple and easy to understand and implement, and they are not very expensive also. Okay, and lot of applications are already there, which uh, which authenticate that these are good controllers, and now this one is a well established technology and being used there. So how this controller works basically, input comes to this controller, and then we have few building blocks inside this controller. One is fuzzifier, okay, in French unit defuzzifier, knowledge base. And when this input pass through all these blocks, it will generate certain output. So like in earlier, inside the block is your P and I and D. Now here we have different things. So instead of taking those things, we have a certain kind of conversions, basically mappings, and then those mappings, they use certain kind of knowledge, and that knowledge, from that knowledge they try to find out the they infer, try to find out what should be the output, and then that output is converted into the real kind of environment. So that is basically the structure of your fuzzy logic controller there. So what is the job of fuzzifier converts your input, which is basically crisp value is real inputs, and it converts into the fuzzy values. So it converts input in from an real numeric value to a value of a belongingness with certain kind of linguistic tags there. So that is the job of a fuzzifier. Just let's define the term so that we can talk later. Knowledge base basically consists of two things, and it is basically we develop certain rules based upon the data we have. That is knowledge base. Okay, most of you are aware of, but if not, then okay, when I am driving a car, okay, I take a I take a decision that how much brakes I have to apply based upon, okay, how fast I am, and then how near is the object to me. Based upon those two, then I make a certain kind of a decision. So I have certain kind of data with me, earlier data, and then I develop a rule that, okay, if the object is very near and I'm very fast, I have to apply very high brakes. So that is basically the knowledge I have. More I perform on the system, more knowledge I have, because I have more data and I can refine my rules also there. So data means like, okay, all the information here. Data is basically membership functions, scaling factors, and all these things, because those are required in developing the controllers there. In the rule base, based upon this one, we develop certain kind of rule. And then there is an inference unit, because it will give you certain kind of, from the rules, it give me certain kind of information, and that information I use to conclude over certain thing. So that is the job is done by the inference unit. And then from there we can have defuzzification, because real world does not understand what is belongingness and fuzzy set. So we have to give the crisp output, so it converts back. So these are the few steps which are being used in fuzzy logic controllers. So how it works? So let's understand with that one how it works there. So this one is my fuzzifier. What is happening in fuzzifier? I have two inputs basically. So the controller, fuzzy logic controller, one input going is your error. What is the error between your desired value and what the system is generating? So that is E. And the second one is CE, that is the change in error. How much is the change in error? Because that is very important, because that controls the dynamics of the system also. And then, okay, this one is basically, then I have certain kind of a membership functions. Okay, so this one is membership function, which is taken as a triangular shape here. Okay, and what happen is this error cuts some membership functions. Okay, so this one is one membership function. Okay, and it cuts at certain value, say 0.8. What is the meaning of this one? This members function represents a certain set. and the name set or name of the set is say ns. Okay, that is negative small. Okay, so it cut its here. So it when it cut its here, so we check it out how much is this value, and this value is 0.8. So this represents that okay, this value of error is having 80% belongingness to this set, and that is the difference between fuzzy set and crisp set. In crisp set, the belongingness is either there or not there. It is 1 or 0. But in fuzzy logic set theory, the belongingness is not binary. It is having a certain kind of a range, So you can see here, the belongingness is 80%. That means this error belongs 80% to this particular set, which is NS. Similarly, this one is also cutting this one at say 0.4. So that means it is having 40% to ZD. That is the meaning of this meaning of this particular representation. Similarly, C cuts these two sets. Oh, okay, and this one is written wrong. Instead of ZD, you can assume something else and some another name. So say PS. So it is cutting 50, it is belonging 50% to PS and 70% to ZD. So this is the first step. So this cutting, this well, if I see if I have added those things here more in more description, I'll explain it. But you can just check it that these interceptions here, they represents that how much this crisp value means my error is 10 degree. That is the crisp value. Here, if they cut it, there is nothing like 10 degree. It is cutting two sets, 80% of NS and 40% of ZD. So we are converting your degree, 10 degree into two terms, belongingness of 40% to zero ZD, zero set, and belongingness of 80% to negative small set. And now these combinations are what are these combinations? This combination means that if now I'm taking row wise, this one is saying that if my NS is there and my second input is 0, then the output is positive small. Okay, so if my NS is if one input is negative small and the second input is 0, then the output is positive small. Now this one is in knowledge, and this one is the rule. This one is rule decided. Okay, and second rule can be if one input is 0, second input is also 0, then the third input is 0. Okay, so this one is the rules. So these rules are designed like this, and then the okay, you have rule that okay, if first input is negative small, second input is 0, output is positive small, then how much of positive small, that we don't know. So there we calculate this thing. Okay, where here in this there are various methods. Here in this case the minimum is being used here. So this one is 0.8 and this one is 0.5. So what is the minimum of these two is 0.5, so that much. So now this rule is complete, that if one input is negative small, the second input is 0, then the output is positive small, and how much is positive small is the minimum value of these two, so that is 0.5. Now this one is the section of inference unit. Similarly, the second rule also give you a second kind of structure. And when then we use these two structures and then we apply an approach to convert it into the crisp output, and that approach is known as defuzzifier output. Now this is the fuzzy logic controller. Pass input, errors and change in error, process it inside, and the process is this first conversion is crisp to fuzzy. So here is crisp and these values are fuzzy. So that is known as fuzzification. Then we have a rule. So rules are there. They decide certain kind of output, that from there we inference it. So that job is done by inference unit. And then we convert it back to the crisp value. That is known as a defuzzification. So this is how the whole process works there. Okay, so there are a lot of things which are present there, and then okay, we will agenda is to discuss more on controller, not on fuzzy kind of how they are working. That needs a different kind of, maybe another professor will explain on those fuzzy calculations. But uh, uh, and if you have query, then last 20 minutes or so I'll kept it for the discussions on that part. So but let's understand on the fuzzy controllers. So the fuzzy controllers can be taken from here, and the first fuzzy controller is like PI controller. Means what? That fuzzy controller which behave like a PI controller. Okay, so you can see here, if I am giving an input to my fuzzy controller as error and change in error, you can see here there are two inputs I am giving. One is error ek, and another change in error delta ek. And if I'm passing these two as the input to my fuzzy controller, and I'm taking the output as delta uk, this one is same as your PI. This equation is same as your PI controller. You can see here. Okay, so this one is same IPI. So if my inputs are like this to my controller, then my controller performance is like a PI controller, and I can call it the fuzzy PI controller. Okay, so you can see here, you can see here. Now these are the gains. I'll come to this one. These are the gains I'm keep on increasing, but you can see here there is a overshoot, and there are oscillations. There is an overshoot, there are oscillations, and it is steady state. And these things are available in that controller also. We have overshoot, and we have oscillations, and we have settling down. Okay, when my inputs I'm changing, instead of taking my inputs like this. Okay, instead of taking my inputs and output relation like this, I have done some change here. And the change is, instead of taking output as delta u, I'm taking output as u. And if it is like this, then this one is same as your PD controller. And if I try to plot this curve, you will find that this one is same as my PD controller. So just changing few things here, we need to be very careful when we are talking about fuzzy controllers. If my, see, you can see here the inputs are same, but in one case I'm taking the output as change in the output, and that will behave like a PI controller. In another case, if I'm taking my output as it is, that will behave as a PD controller. And many times this type of mistakes we do there. Okay, so that this one is your PD controller. And then if you do the change there, input change, if you give input error, change in error, and sum of error to your controller, then the controller will behave like a PID controller. Now you can see here fuzzy controller is, so what we are doing, instead of giving delta ek, what I'm doing is delta u is function f, fuzzy function of error, was one step earlier, which is basically can be taken as a change in error, and then 2 step earlier, which can be considered as a summation series of kind of structures there. So this one is like a PID controller. This one, these are the screenshots taken from fuzzy inference system, which is available in MATLAB. Try to simulate it there. The behavior is like a PID controller. Okay, so this is how you can make your fuzzy controller to look like, to behave like PI controller or PD controller or a PID controller. The issues are there, and again issues are some tuning is again required in fuzzy controllers too. It is not like, okay, we don't need any tuning in fuzzy controller. And one kind of a tuning is adjustment of parameters, and we can do it by two ways. Either we do some scaling of input and outputs, or we do some kind of operations on fuzzy memberships. Okay, what I'm assuming right now is you are much aware of all these terminologies, membership functions and type of membership functions and all these things. So uh, if not, then we can have a discussion in the query section. So we monitor the things, what are the changes. So we process monitor, sense the changes which are taking place in the process characteristics. So we can make it like this. Okay, we have fuzzy controller. We sense what are the changes occurring, but depending upon the input only, we can make the tuning of here. And we can do the changing process two ways. Either we sense the change which are taking place and then modify it, or we receive signal from the process monitor and alter the system parameter on the basis, depending upon how you are considering it. So we have two structures. Okay, one structure is just we sense the changes which are happening and modify the control parameter. Second is okay, you take the input, sense the changes, you take the output of the controller also, you measure on the certain parameters based upon your adopt some adaptation mechanism, and that adaptation mechanism change your controller parameters. So we have two type of topology, both comes under the category of adaptive fuzzy control. This one is one kind of adaptation, this one is another kind of adaptation. This is not working. Okay. So adoption mechanism and scaling factors. So if I'm just varying my scaling factors, okay, I'm just changing the scaling factor. Scaling where we need, we do the scaling at 2 points. One is the input scaling and another one is output scaling. What is the meaning of that? That when we are passing an input to a controller, it is multiplied by certain factor. That is a gain basically, or scaling factor. That is input scaling, input gain, and output scaling is that when the output is generated by the controller, we multiply it by certain gain. So we have three gains: error and change in error gains when we are giving the inputs to the system, and the output is output gain. So we have good and bad things which will happen. Like if we take high value of gain related to error, it will result in responsiveness of the system, that is low steady state error and rise time. But the stability is poor. If I take high value of error gain, change in error gain, it will give me fast convergence. If I take a low value of output gain, it increase the rise time and integral square error. So these terms are related to control system like steady state error, rise time, stability, and all these things. So depending upon how I want my system to behave, that can be seen from by varying these gains there. Like or you can select these gains and make it an optimization process. Okay, so I'm just giving two kind of structures. This is one kind of structure, you just play with these gains. Second one is your adaptation mechanism. So you measure certain kind of performance. Let's go back to the slide here. Performance measure, you decide, say I decided that performance measure is steady state error, and the adaptation mechanism is minimize my steady state error. Okay, so that will come here, you can see here minimization of steady state error. So you will see there in the graph, there is no any steady state error. But if you zoom it, you will find certain peak is there. But if you decide that, okay, my performance is minimization of peak overshoot, that means there should not be any peak here. It should be always less than 1. You can see here the graph will be like this. It is always less than 1, but there is a continuous steady state error. So this one is adoption kind of structure. This one is you adopt a certain kind of a rule there, that okay, what is going back to the same figure here, what is this performance measures you are putting in. So performance measure, if you are saying that okay, performance measure for me is peak overshoot, adoption mechanism is okay, minimize peak overshoot, so then the performance is different. If the performance measure is steady state error, and then adoption mechanism is okay, minimize steady state error. And here what we are doing, we are controlling the scaling factors. In that we are varying the scaling factors so that we can reach to this count. Okay, so we have one approach, this one we just modify it. Second approach is this one, which is much better. You set your performance measures and then follow certain kind of adoption mechanism. In this case, what we are doing is we are adopting by using scaling factors. Okay, so this one is one way of doing this thing. Second way of doing the things is by playing with the membership functions. So can we have a all those things what we have process monitor, and then we have performance measure. But in first category, in this earlier slide, what I've shown you is what I have done there is okay, I achieve my performance by varying my scaling factors. In this case, I have changed it. I'm not varying my scaling factors. What I'm doing here is I'm changing my membership functions. And that is very interesting. And why from where the idea comes in, I'll explain to you, and how it is behaving that way. Say when you this is screenshot I have taken so that when I can show you. Initially, when I divide my whole space for error in the range of -1 to 1, okay, and I have decided that there will be 7 membership function, because when my machine starts, or when my robo starts, then at that instant the error is maximum, because the robo is at angle 0. I want to rotate it 30°, so that is the maximum error. When I pass the command, it keep on reducing. Okay, so so this is the error range -1 to 1, and this is maximum initially. But with time, what will happen? This error keep on reducing. Finally, it has to be 0 error. So if it is reducing, so say after certain time, in if say my error is -0.4, then there is no point, or say -0.2. So then there's no use of B1 and B2 as such, because they are out. And you can see here we are in a zone where we are only governed by only one membership function, which is not a good idea, because that gives us the zone of error. So what the idea here is, initially we start with this whole spectrum -1 to 1, and what we'll do is, with time, if time is changing, with time error is also changing, why not to change these membership functions? So you can see here all membership functions, they are squeezed in a zone of -0.5 to 0.5, so that this one is kind of zooming in. Like initially I have a big error, so I have big view, and then with the time my error keep on reducing, and as it is reducing, then what we are doing, I'm pushing all the membership function into particular zone, so that I can have kind of a interesting kind of analysis. I have more coverage over things, and if it still reduces, then I push all the 7 there inside that particular zone. So that's a basically adaptive fuzzy controller. Now the earlier one, slide number 27, adaptation is on the scaling factor. Sorry, adaptation is on the scaling factor. Here the adaptation is on the membership function. Now there are two ways to do it. One way is I keep the symmetry of the membership function as it is and push them to the narrow region like this. This, if I follow, such type of controllers are known as symmetric adaptive fuzzy controller, because the membership function, the shape of the function remains as it is. We are not changing it. There is another category. Okay. Okay. So you can see here, these are the symmetric membership, and it changes for all error and change in error, something like that. Okay. These are the rule. What is the rule? Changing the rule positions and all that, and the surface position. And this is the performance. The performance is very nice. It like okay, it has a very good performance towards the end. Like you'll find it's working very good. Then there can be another category of this one, and what is that? Unsymmetric. That means what? I'll show you here. Better picture. Yeah, this will give a much better picture. That is, this bottom points remains, one point remains same there, means like one point is fixed or some kind of that one. Now the shape is not not taken as it is. Okay, one point is fixed and the second point is moved. So either of the point, either the bottom point is fixed, top is moved, or the top is fixed, bottom point is moved. So if you do so, a number of membership function remain again 7. Here it is 7. This one is initial, and this one is the final right hand side. So final we have again 7, but you can see the shape of them. The shape changes because here we are changing with membership functions there. Okay. So when you do so, you have again different kind of rule based, different kind of surface, and then different kind of performance here. we have observed for lower gain values, we have some over peak overshoot also. But this is one kind of a experiment I have done to see that, okay, what is the effect there. We'll discuss on those parts later. So these are the two and two, three. These are two different categories when we are changing our membership functions, changing the shape of our membership functions. We can have more analysis on the types of membership functions and likewise, and some kind of hybrid combinations also there. But this is how you can make it adaptive. Now these changes are automatic, means like we are not putting any kind of manually doing the things. Based upon your error and change in error, it is being done there. Okay, so this one is one kind of this one. There is another kind of a controller which is basically neural controller. Okay, moving a bit fast on that one. We know that how neural network works. They are inspired from biological neurons. We have synaptic operations and somatic operations. So initial one is MCP, which can be designed like a neural controller. Okay, so we have input output weights and weighing factors. We train it. So there is a similarity. This one is MCP kind of. This one we have inputs as a we are taking inputs in biological neuron. Here also we are taking input, but in this category neural controller, the inputs are error and change in error. There also we have weighted or amplified signals. So here we have weights there, then we have summation sign, and we have a nonlinearity present in the system. So this one is same as a means the structure is same as a neural network, and now this one is being used to design any controller there. Okay, so what is architecture arrangements of the neurons? We can have single layer and we can have multi-layer. Both can be used there, depending upon like complexity level you want to design for it. So multi-layers, if you want to go for it, you can go for it to have different kind of analysis on the structures. We have architecture based upon neural processing. We can have feed forward and feedback networks also, and we can have unsupervised and supervised. So this category, what we have studied in ML or
Okay.
neural network course in undergrad classes or grad classes, same theories can be used here. The only difference here, inputs are your error and change in error. Output. Yeah, any question from your side?
Okay, ma'am.
Shubha, I think.
Yeah, somebody has unmuted. Okay, anyway. Okay, so the same theories can be used there of training and supervised or unsupervised architecture, but
ಸ್ಟೂಡೆಂಟ್ಸ್ 3 ಜನ ಲ್ಯಾಬ್ ಅಲ್ಲಿ ಇದ್ರು ಸರ್. ಅಂದ್ರೆ ನಾಳೆ ಟೆಸ್ಟ್ ಅಲ್ವಾ,
Dear
ಹಂಗಾಗಿ
participant,
ಬಂದಿಲ್ಲ.
please
ಅವ್ರಿಗೆ
mute
ರಿಪೀಟ್
yourself.
ಮಾಡ್ಕೊಳಕ್ ಹೇಳಿದ್ವಿ. ನಿಮ್ಗೊಂದ್ಸಲಿ ತಿಳಿಸ್ಬಿಟ್ಟಿರೋಣ.
Just a second, sir.
ರೆಗ್ಯುಲರ್ ಮಾಡ್ಸಿದ್ರೆ ಮತ್ತೆ ವಿ ವಿಲ್ ಹ್ಯಾವ್ ಟು ಕೀಪ್ ಆನ್ ಟೀಚಿಂಗ್. ಅದಕ್ಕೆ ರಿಪಿಟೇಷನ್ ಮಾಡ್ತಿದ್ದಾರೆ 3 ಜನ ಹುಡುಗರು. ಇನ್ಸ್ಟ್ರಕ್ಟರ್ ಇದ್ದಾರೆ, ಡೌಟ್ ಇದ್ರೆ ಕರೀರಮ್ಮ, ಬಂದು ಹೇಳ್ಕೊಡ್ತೀನಿ ಅಂತ ಹೇಳಿದೆ.
पाटी जी, अरे म्यूट करो यार, एक चल रहा है मेरे को दोनों एक्सेस. अरे हट गया पता नहीं अपने आप, तो देखो जल्दी से.
ಎಲ್ಲಿಗೆ ಹೋಗಿದ್ರು ಶ್ರೀದೇವಿ ಮ್ಯಾಮ್? ಪ್ರಸಾದ. ಓಕೆ.
shall we now?
Sir, just wait, sir. I am taking access. Actually, somehow the access is gone from my side.
Yeah, it's okay. It's okay. You do it.
Okay, sir.
मैंने होस्ट बना दिया सर आपको.
Okay, okay. Sir, now we can start.
Okay. Thank you.
Thank you.
So here, whatever we have studied in your neural networks, those things remain same. We can have any type of network like feed forward or feedback or supervised or unsupervised, any kind of structure there. The only change when since we are talking about the controllers, so we are taking the inputs either what is desired and what we are getting. Based upon that we design, or what we can do is we can check take the input error and change in error, and then we take the output. Okay, output can be the desired trajectory, or output can be the performance measure there, that okay, what input are changed in error, and error and output is like certain kind of a steady state error or something like that. So depending upon those things, we try to map it, and all those theories which are there, those things will work there. And then yeah, we use back propagation to train our networks and all that, so I'm not going repeating those things which are already aware to you in neural networks and all these things. But yes, here we can have one kind of a controller architecture which is there in front of you. So I am taking 3 input network. This one is one of my neural controller. So one input is my error speed, what is the desired speed, then the second one is the change in the speed error, and the third one is the change in speed error. And based upon that, the architecture is designed. And then yes, you can see here there are various layers, and then we have these equations which are same as in case of neural network: input into the weight, and second input into the another weight, and third input in the weight plus biasing, and likewise we have no linear mapping there, and output is there. So that thing is same. We need to see that okay, what are the inputs and outputs in our case here. So we can take it, we can perform various kind of experiments there. One of the experiment is which was done by me is like, okay, let's fix your learning rate. So we have certain kind of structure there. You can see here the response is quite good in all these figures. The desired value is 1. And then okay, you can have adaptive learning rate. So you can have variation in learning rate, you can make it adaptive. You can make your learning rate as a function of certain thing, which may be a function of time also. So you can see ultimate goal is, can we make this graph like more sharper, rather than making it is like this? Can we have a very quick response and settling at 1? So there, okay, we can take some kind of relations which change my learning rate, because here in back propagation and all those structures, you are we are aware of that. Okay, when you try to modify your weight, it is a function of the learning rate. So how you can make your learning rate adaptive? Okay, so now the things comes in, but yeah, neural network has certain kind of advantages and disadvantages. Fuzzy has an advantage and disadvantage. Advantage is it's robust, it is more stable network controller. Disadvantage, it has certain zone of error also in neural network. Zone error is less, but at the same time we need a uh, good data to design a controller for a particular process. So we must have a to understand the information of this to understand more about the system, we must have a good number of data, so that we can have a better network. So if people try to make it a combination of this, that can we combine neuro and fuzzy, and from there a neuro fuzzy architectures comes into the picture. So this one is basically using the knowledge and the learning ability, and these two approaches are being combined so that we can have better configurations. Okay, so they are well suited for the system where the user interaction in the model is desired, and at the same time we want to modify our network equations and mathematics there. There are two groups. We need to understand it very clearly. There are two groups there. People get confused, and sometimes one group is fuzzy neural networks, and another one is neural fuzzy inference system. So you just focus on that which comes first, fuzzy neural network, and another one is neuro fuzzy system. Both comes under the category of neuro fuzzy inference system, and here is the difference in front of you. This one is fuzzy neural network. Okay, so you can let me read out these things, because these are very important. The characteristic of each synapses is represented by a nonlinear function, and the aggregation of synaptic is done by an algebraic sum. Okay, so you can see here in this structure, if you watch it carefully, we have inputs, then in neural network we have weights here, and then they are summed up. Okay, Now in this case, you can see here, the weights are, these weights are no more weights, they are functions basically. And these are fuzzy functions. So if you are having architecture like a neural network and whose weights are like fuzzy functions, that network is known as fuzzy neural system. And the controller, if you are processing in a control, that is known as fuzzy neural controller. So that is the important thing there, which is here in this category. In second case, that is neural fuzzy inference system, you have structure is something like this. This is kind of, you can see that this structure is a bit different, whose nodes have a different processing. So look like a neural network kind of things there, but yeah, layer 1 job is it is doing fuzzification, layer 2 is rule based, layer 3, 4, 5 they are defuzzification. So we need to see that how we are using these functions. So in this case we have layers, each layer is having a particular job, like one layer is doing fuzzification, second is developing the rule nodes, third one is doing the normalization, another one is consequence layers, and the summation layer, and likewise. And if the things are being made adaptive, we call it NFIS, which is very popular approach, and controllers are being used known as adaptive neuro fuzzy controllers. Okay, so here you can see here layer 1 is your adaptive nodes, okay, which is represented mathematically like this. Okay, layer 2 they are fixed nodes. So you can see here variable nodes and fixed nodes. Okay, the equations are there in so output of adaptive node is you give the value x and it will generate a membership functions. So you can have it here. Then you have another node which are fixed node, which represent the firing strength of the rule. Okay, third node is again, and it's a normalization node. Fourth node is a adaptive node which parameterize the things. And then fifth is again a fixed node which calculate the overall output of this thing. So this one is the structure of NFIS nodes. And then okay, we use update the parameters using gradient descent, and if your problems are still very complex, then you can think of update of weights by using some other approach other than gradient, maybe modified gradient or fast gradient, and anything like that. And then okay, we use your backward pass, forward pass, and all these things. So I'm not going to that mathematics here. What is forward pass and backward pass? Okay, forward pass and backward pass is nothing but the training, how you modify your weights there. Again, the modification can be there because in this case, going back to the figure here, sorry, let's skip few things here. We are better to go here. Yeah, we are what we are having here. We are having fuzzification, so we can play with the membership functions here, or we can play with the scaling factors here. Here are the rules. Normally, since if it is fixed, so we cannot do anything here, but here we have again some kind of variability. So in backward pass, there is nothing like to update our weights. What we update is their membership functions or their scaling factors. So what we have done in adaptive fuzzy controllers, those things in a different form, they are being used here in neuro fuzzy controller. So that's why we are saying adaptive nodes, we can do some changes, and we can do some changes here, membership functions and the types and shapes and all this. Fixed node, they are fixed, we cannot do much change there. Then another set of fixed node, we cannot do any change in backward pass also. Then another, it's a fourth layer is adaptive, where we can play with the parameters. So we can play with the parameters here. And then last node is fixed, we cannot do these changes there. So when we are doing back propagation, we cannot do any change in the fixed nodes. So we have only at 2-3 places we have adaptive nodes where we can perform the changes. And what are the changes we can do it? All these are the same. You can change the rule of the fuzzy set. You can change the shape of the fuzzy set. You can vary the position. You can make them symmetric. You can make them unsymmetric. So whatever we have discussed earlier, the same thing you can do it in backward pass when we are talking about NFIS. So these are the certain results which are obtained like NFIS. S means symmetric. So membership functions, they are varied symmetrically. So you can see the performance of the curve there. And then unsymmetric means their shapes are controlled. Their shapes are not fixed. They are varied kind of structure. So now I'm taking the moving towards the last part of it. Let me make you understand this figure, and then we can come to the rest of it. So this one is, in this case, this one is the basically what I want. I want my machine to run. It's a 3-phase machine, big machine. So I want my machine to run at this speed. So I give this command, computer at this speed. Okay, you keep on running. And at this instant, I give a command. Okay, run in the opposite direction. So it should, instead of this, it has to move in the opposite direction. So this one is speed curve. Okay. So what will happen? Motor machine has its inertia. So it starts and then settle very fast here. You can see this timeline not clear on screen. It is 1.1 seconds. So it settles very fast, remain there. At this instant, I'm making it, okay, move into the opposite direction. So it start moving the opposite direction and settle very fast in the opposite and remain there. This is supported by the current. These are the 3-phase currents. So you can see that, okay, initially the motor is taking in the transient, it is taking more current so that it settle down. So you can see that more current are there, and then you can see here it settles at the required speed. So no high currents are required at this. So we call it no load currents. There's no any loading on the motor, and at this instant I'm putting a sudden load on the motor. Okay, so I just connect some load to the motor. You can see there is nothing in the speed. This is because of the controller there. But if you are putting load, it can be motor. What will motor will do? To run the same speed, it will draw more current so that it can remain in the same speed zone. So that can be observed here till at this point, because from the speed curve we cannot observe that motor is loaded or not, but from the current we can see that at point 2 the load is there, so it is taking more current. And then since we are changing the direction of motor, so it needs more current. So you can see the current is more here, and you can see here how we change the speed of a motor in direction of motor. We need to change the sequence of the current. So you can see the sequence of the current is changed here. The third one is the torque. Torque means like, okay, how much the torque force is generated. So initially we need a high force to run the motor. Once it is in steady state, it remains as it is. When we load it, we need more current, and then if you want to reverse it, you need a torque in the reverse direction so that it can be reversed. Well, this one is one sample of it, and then okay, to understand it much better way, we zoomed it. We zoomed this section so that, okay, what are the oscillations in the speed? So these are the oscillations in the speed. Okay, this one is 314 and this one is 314.005, and likewise. Similarly, how much is the torque oscillations? We zoomed this section, and then what will happen if I suddenly put a load here? Putting a load means when you put any load on a motor, running motor, its speed goes down. Its speed goes down, but if you have good controller, it come back it very fast. So nothing is clear here, but when I zoom it, you can see when I put a load, its speed goes down and very quickly it come back. Similarly, when I remove a load, it will have a jump because you have removed the motor. It increase the speed, but it has to come back. So this one is basically just to see that how it is behaving, and then to analyze it whether my controller is good enough or not. So here you can see here, in this case, it goes down to a value somewhere from 314 to 312 because you have put a load, but very quickly it come back and it retain there. So these are the certain graphs, and then we analyze these graphs. So you can see here, this is the graph which is very important, which is zoomed version of this from point 15 to 0.35 of this from of the speed curve, where we are putting a load. This is most important thing for us. So you can see here when the load is put, it jumped down from 314 to somewhere 311, moves retain very fast, and then when the load is removed, it moves from 314 to 315 and comes very back. That means when if you add a load, remove a load, the speed remains almost constant. If there is variation, your controller is good enough to retain it back so that the machine comes back to it. It can be since here this one is a drive rotating machine, it can be a robotic machine or something else. Your case can be anything like that. Now coming to the last section of this whole discussion, that is basically how you check the performance. So one way of checking is this one, that okay, so these are the various controllers which I have simulated for the same problem. We started with PI and then PID, self-tune, fuzzy tune, neural tune, genetic tune, slide modes, then fuzzy PIs, and symmetrical, unsymmetrical, neural, and then NFIS, all the controllers. So one thing is how, if your machine is steady state, how much ripples are there. So you can see here, mm, here this one is poor performer for PID neural tuned, because we don't have that much of accuracy in the data. So maybe the neural network which we have designed to tune my PID is not good enough. And fuzzy is most stable, I told you that. So it has a very good results. You can see the variations are very less, variations in the speed. The speed is almost constant speed. Similarly, unsymmetrical fudge inference. When I talk about the torque ripple, yeah, slide mode, since slide mode is having chattering kind of issues and all these things, those are reflected in the torque, and the ripples are maximum in the slide mode, and they are best in your NFIS, symmetric NFIS. So best means very less torque ripples. So this is how one way you can see that how your machine physical properties, they are, yes, they are physical property, they are behaving when you are using certain controller. You need to see what the transient response also. So I have tested all the controllers with different types of transient response. We have four main. One is what is the starting time. That means we start it, and if it reach that to a certain value, how much time is required for that one. Second is reversal time, how much time is taken to reverse the direction speed. Third one is dip in the speed. When I load it, how much is the dip? And fourth one is when I remove it, how much is the rise in the speed. So poor performance is PI, but yeah, PI self-tune performed well here. Neural network also performed very well. These two values are same because we have used this PID self-tune data for to train this neural network. That's why the performance is same. When you reverse it, okay, in that category, your slide mode is not good enough, but yeah, your fuzzy, unsymmetric fuzzy is performing good, and neural is also performing good. If you talk about the dip in the speed, PI is having less dip, whereas PID neural tune is having more dip there. Similarly, the rise in the speed. So this give me the performance if I would like to see what is the transient effects on my motor. Then there is another kind of category, extension on the transient response, and this one is very important. Now this one is from power, from control system point of view. These are the parameters which are very important. Peak overshoot, that means if I give the value 1, how much it is going. Okay, then peak time, how much is the time taken by my motor to reach that particular value. Or you can take it, okay, I'm controlling my robotic arm, so there is a motor. So if I give angle 30, so overshoot is how much it goes beyond 30, or likewise. Peak time is how much time it is taken to reach to that peak value. Rise time is basically my fast response, how fast I am reaching there. Settling time is the time required to settle. There's no oscillation, steady kind of this. Steady state error means if it is required 30, what is the angle taken by the or final angle attained by that particular robotic arm. And these are the performance parameter: integral square of error, integral time absolute error, integral time square of error, integral absolute error, and this one is another domain, summation of last 10 errors kind of structures. So these are the responses of the various controllers, and you can see here PI is poor performer in the peak time because you can see it's not reaching peak overshoot, and I mean it's like it has certain kind of peak PID is having much more value there. Very obviously, it is taking more time because it is taking more time, and the overshoot is less, whereas PID is having another kind of value which is a bit faster, but the time is taken is less. So that means if it is taking less, and since the motor is having inertia, or very obviously it go beyond the peak value. So that's why the overshoot is more, and your time is less. So likewise we can have analysis from this thing, but all these cases we have steady state error 0. So there is one kind of a comparison that which one is performing faster, which one is giving me jerks, which one giving me errors, which one is showing me overshoot. And at the end, we can make a decision on the controller on the basis of these parameters that, okay, which controller is good for me. So these are the other categories like fuzzy categories and all these things. So which controller is good for my purpose, and which one is giving less peak, faster response, less steady state error, and likewise. So from there we can make a conclusion like, okay, which controller is used for, can be used for my particular problem and all that. So there we can conclude in a simplified manner, that is intelligent PID controllers are easy to tune because it's a good combination of intelligence and your conventional controllers combinations. Yeah, slide mode controllers, they are robust, but chattering issues are there. Fuzzy controllers are the next category, and that's why they are more robust, and that's why they are more popular, being used in your cameras, washing machines, and everywhere. Uh, if there are tuning issues, they that can be eliminated by either making them adaptive, or you can use certain kind of tuning approaches. Uh, and you can think of more hybrid controllers that those can be designed and can be implemented to your problems. So yeah, I think yeah, we have 10-15 minutes, so I stop it here, and then take questions from here. If you have any questions, please unmute and push your questions so that I can answer your queries there.
So dear participant, if you have any questions, please ask to sir.
Yeah, you can put it into the chat box or unmute so that I can answer your questions. Any question related to controllers, intelligent controllers, or anything? You're most welcome. This one is very simple way. You take any microcontroller and develop any rule-based fuzzy controller, and then burn on it, and then you can implement it. It works very fine. Just you need to do some kind of a refinement on the tuning process. Whereas if you are using PID controllers and all that, and you're thinking of building a hardware, yeah, you need to see of your op amps and their calibrations and all those issues there. Sometimes they work fine. Nowadays we have chips, no doubt on that one, but what I'm thinking of, like, if you want to develop of your own, then okay, these intelligent controls like fuzzy and all these things, they are much simpler to implement, and people are doing them using them for their various processes. So any question? Yeah, how to implement a fuzzy logic controller in simulating environment? Yeah, Yeah, Munish, this one is easy. I think there is some another lecture on it, where you can have hands-on. Otherwise, you can visit my website. There I have put one PPT how to practically you can want to implement this FLC in MATLAB Simulink environment. I post to you here the link so that okay, if you want to do it, you can have it from here. Just give me a second. So you can visit this you can visit the website, and there I have given a put one presentation that okay, uh, uh, how to implement it, and you can put it. What are the options to implement FLC in hardware? Yeah, it's easy. I told you, like okay, you develop a rule based kind of a structure there, and then okay, whatever controller, microcontroller, or processing unit, processor board you are having, you just implement it out there. Okay, so set theory is not a big thing to implement it in terms of mathematical forms, and then from there you can do that first part of his fuzzification, and then the rule base you can take a say simple structure of 3 by 3 structure. So I can have a 3 membership function for error and 3 for change in error. So I'll have a 3 by 3 and 9 rules, which is also very simple. And then defuzzification, you take a very simplest one that okay, first maxima. So that makes your controller very simple and light, and you can build it on any process on any processor where you can have a processing calculations, and then you can just put it. They are open source. You can use many open source like uh, you why not to code it in a programming way rather than using the boards there, like uh, in MATLAB Simulink you have that FLC that process it opens for you, and then you can do it. No any issue in that one. But the good idea is you can program it in a very simple way, like okay, I want to develop a member C function. It is nothing but y is equal to mx plus c. So I'll take from 0 to peak mx plus c, and then peak to 0, negative of that one, and then I apply a shifted property. So just 3 equations can develop all types of member C functions for me. So if you do the programming that way, I think then things become much more simpler, rather than if you use their inbuilt toolboxes and try to do it. That takes a lot of time and likewise. And that's my suggestion. It's better if you code the things and do the coding in M file, and then burn it on some certain kind of a processor board. I hope means I'm able to clear few of the things. If you still have doubt, then my mail ID is there on that website, so you can push me a mail. I'll give you the details. Okay, in means how you can do all those things for a particular purpose. Yeah. Any more questions?
Sir, one question from my side.
Yes, please.
So why we are using most of the time fuzzy PI, RPI type of controller in drive application?
Yeah.
In-
See, PI is the most robust and easy in the sense like okay, what we assume there is nothing like noises and all these things. So why to put another gain? So we kill the derivative term. So we left with PI, and if I remove I, P is having a problem because it never like eliminate my steady state error. So I have to keep I with it. So that's why PI is the most popular controller, which is common throughout the industry, robust one. Issue is only with the tuning of this PI, and because we have to find out the most optimal weights there. So since it is robust, fuzzy itself is also robust. So the fuzzy PI is more robust. It's the combination one we can say. Whereas in fuzzy, we are adding those terms where we can adding the vagueness and all these things. Like in PI, it's not vagueness. PI is purely 1 point to 1 point, kind of pure classical set you can think of. That okay, these are the parameters of the system, then PI perform better. If there is some change in the parameter of the system, PI has some issues there. But fudgy PI can take care of those issues. The vagueness or model vagueness, if it is there, fuzzy PI can take care. But if model weakness is there, pure PI cannot serve better. So that's the point, like why people are using, mostly they are using PI.
Actually, sir, I have seen in your PPT you also used fuzzy PID in some of the drive application. So is
Yeah,
it not giving better performance or what
I have
are
tested all. I have tested the whole series.
okay.
With from P, I start with PE and I end up with NFIS also, just to check it that okay, which one is performing better and why it is performing better, and for particular application of this thing. So in PID, like okay, uh, if you compromise or if you can put certain kind of like in invest on attaining one more gain, then okay, we can kill those things, like if there are sudden changes which are in some cases not required. So the derivative term stabilize my system. So in that scenario, D is better, because whatever, if there are certain kind of sudden changes, it kill those changes, which sometimes we also try to avoid it. So that's those scenarios, your uh, we can think of like, okay, let's put extra cost on the derivative part and add it to the system. So that's why PID is being used there. So depending upon the application, what type of application I'm looking for, and how much I can think of like investing or looking for the complexity or the type of the system or variability in the system or the dynamics of the system, we can make a balance on those things.
I think it also increases the hardware complexity when we are adding deep.
Yeah, we have an additional term, we have an additional component we have to put in, and then obviously that increases the hardware complexity. And then yeah, many times there are some certain other issues related to the, like okay, I'm using it for a simple drive, it's okay, but if I'm using the controller for some high frequency operations, then those high frequencies may affect your system controllers, they can interact with this one. Well, a lot of things can be think of when we put it on the real system and then how it is performing. But yeah, PID is the more simple, is the best, because it contains all the three. But sometimes I don't like the third one, so I'll take PI. And sometimes my operation is not, I don't want very much accuracy, steady state, and then I can think of simple K. Okay, let's go for the proportional one, the easiest. Just put one gain, it is very fast, and it is like like a level controller, either this or this. So depending upon my accuracy, my performance, we can think of all these controllers.
Thank you, sir. I'm one question, sir. I'm getting general question like how to do PhD in MNIT in under your guidance. What are the procedure for that? If anyone
Okay.
is interested.
Okay, I would like to share. I'm working in the domain of machine intelligence and data analytics and robotics. Procedure is the same. The procedure is we already have call for PhD admissions. Last date is 16th of December. So you need to fill your application. While filling the application, you need to take care that you have to give 3 or 4 choices in which area you want to do. So if you want to do with somebody, like okay, you want to do with me. So every year faculty, they announce their domain. Okay, next 2 years or 3 years they are going to work in this domain. So check those domain, and while filling the application, you need to write down those domain in your application form. Once everything is done, then there will be exam uh, at maybe in Jan. There are 2 level of exams nowadays at MNIT. Morning we have exam on language and analytical skills. So there we have like basic mathematical questions, like IQ type questions, and language question. One student cross that one, I think there is some minimum requirement. Okay, if you score this much, that we need to check it. Okay, I think it is around 40% or something like that. Then in evening there will be another exam that will be related to the domain, means domain area. And after that the select um, shortlisted students, they called for the interview, and then the person what they have applied for. Say somebody has applied for robotics, so then the person who is in the robotics, he will interact and ask questions, and that's all. That's the way of institute scholarship PhD admission. In another another is okay, through projects person come, but to do a PhD, again he or she has to follow the same procedure. So the procedure is set by the institute, and anybody who wish to take admission at MNIT, uh, they have to go through, he or she has to go through this whole procedure. That is the way. But other than this, yes, it can be done, like joint supervisions and all these things. Like, okay, you wish to do PhD somewhere else, and there is one expert of particular domain, and you want to combine two domains. Okay, say say at a triple IT quota, the candidate wish to do a PhD, but he want to combine machine intelligence, and I want to combine, say, robotics. So say you are the expert there, machine intelligence, so you can be a supervisor, and a person from MNIT, like, okay, say I'm taking only my case, so say I'm there, I can be joint supervisor, and people do that way also. So there the rules will be rules of triple IT quota will be followed, something like this. These are the various ways where how the people, students, they take the admission in various institutes.
Right, sir.
Hello.
Yes, please.
So one question from my side.
Yeah.
Why we used a fuzzy PID controller as a fuzzy PI plus fuzzy PD controller?
Not we are not using fuzzy PI and plus fuzzy PD. What we are using is we are using the three inputs in a fuzzy controller. Okay, and those three inputs are error, change in error, and then another one is sum of the errors. So if I give these three inputs and I use a fuzzy approach on it, then that controller will act as a fuzzy PID controller. So we have three terms. If you go back to those slides, we have error T or K, because samples if I'm talking about, and then ek minus 1, and then error ek minus 2. So if I take these three as inputs and design my controller whose output is I'm taking to control any process, then that controller is known as fuzzy PID controller.
But can we use fuzzy PID controller with the two inputs?
Fuzzy PID controller with two
Error and with a rate of change of error.
Input is always one. Okay, input is always error, but inside the box what we do, we put a one delay that will create a error team. We put one delay and then compare those two, that give me change in error. Only input is always one, that is always error. What is desired, what we are getting, that is the error, that is the input which is going. Then what we will do, to that particular input we put one delay. So if the delay is there, and when again I compare those two things, that will give me the error ek minus 1, and then we can take keep on adding those errors. That will be the third component. So component going inside that whole block is only one thing, but I'm talking about the mathematics, what move inside the fuzzy. We have to give three inputs: error, change in error, or sum of errors. So that can be considered or rewritten ek minus 1 and ek minus 2, and that will act as a fuzzy PID controller.
Okay, so one more question.
Yes, please.
Which controller performs better in fuzzy PID and fuzzy PID with derivative filter?
Okay, so why you are putting a filter there? Let's take it from there. Why we are putting a derivative filter there? Additionally, if I have derivative term there,
Yeah.
so if I have PID, so why I'm putting another derivative term there? See, you understand in this one in control system, the addition and deletion of these derivative and integrals, they affect the stability of the system.
Okay.
If I keep on adding the integrals, if I keep on adding the integers, the stability move towards the means the system become less stable. If I keep on adding derivative terms, the system become more stable. But if I keep on if I increase the derivative terms, so what will happen? Any change, any noise which comes into that particular loop or calculation, it will be amplified.
Okay.
Because your derivative is the change of the signal. So if there is any change, and that is multiplied by gain, so if I have more terms there, every time it is multiplied. So we never want a system to behave like if there is some change. Say if there is some change because of the fluctuation of the light or power fluctuation, now it since the controller is there and derivative gain is very high, so there is some change and that change is amplified. Then we don't want that. So we have to make in the system like that only.
Okay. Thank you so much, sir.
Yes, please. Thank you. Can we use fuzzy logic controllers in optimization problem? I think, Doctor, better will be use optimization in designing fuzzy controllers rather than using fuzzy logic controllers in optimization. Well, in some kind of a processes, some kind of optimization, you can use fuzzy logic approaches to design those optimizations. Say, that's not a proper and appropriate, but I have seen few of the articles people have written that they have used fuzzy controllers in getting or tuning the parameters of your optimization problem, optimization algorithms. People have done. You can do that also, like we have done. If you go there, like okay, in PSO, I think most of you are aware of partial swarm optimization, but if we go by the original one, maybe the convergence is not so good, but if I do clustering in there, apply clustering approaches, then okay, I can have much better results. So if my my optimization algorithm which you are designing, it is having certain kind of vagueness, and you want to incorporate that vagueness, or you want to incorporate your expertise knowledge base, okay, there you can use fuzzy logic in your optimization problem also. That there you can use it, but fuzzy itself is basically vague, works on the vagueness. I don't think it's a good idea to put that okay, the results obtained from this one is optimized one. But yeah, the vagueness, to address the vagueness in the suppose you are proposing some optimization algorithm where you want to incorporate the vagueness or expert knowledge, okay, to address that particular section, you can use your fuzzy logic. And if you are controlling some parameter of that parameter in that particular optimization problem, then you can use fuzzy logic controller also. Yes, anything more?
So I think all the questions are successfully handled by sir. So sir, you have covered almost all the from starting basic from PID, P and fuzzy PID and everything, and then neural network, and also you have covered about some tuning things also. So I think if the participant has knowledge about that, they can easily implement those things in their respective areas. So thank you, sir. Thank you, sir, for your wonderful session.
Yeah, thank you, Dr. Anupam, for introducing me to so many wonderful audiences there. And yeah, I'll be happy to see that if anybody wish to work in the intelligent controllers and all that domain, I have already shared one link. My mail ID is there. So if anyone has any type of query or questionnaire, yeah, you just mail me and wait for 1 or 2 days. Within a 1 day or so, I'll reply back on that. Yeah, thank you.
Thank you, sir. Thank you very much, sir.
Okay, thank you. I think.
So next section will be start around 11:30. So all the participants requested to join on the join at sharp 11:30. before that. So thank you. We will meet again at 11:30. Thank you. I will share the feedback link in the chat box just now.